Hey everyone, welcome. We are in IC, and our goal right now is to get some more problems done on our study guide for the unit test that is coming up this Monday and Tuesday. So if you take a second to check the calendar over here, the test is going to be on the 23rd and the 24th. After that point, after we take our unit exam, we will be solely focused on studying for your final study guide. So we'll be doing that in class, and we'll also be studying for the final during IC, and if you come in at lunch, I'm more than willing to help you. All right, so for now, though, I do want to make sure you guys notice that there was a change to number 7. I had to add some information in number 7. The density of the solution is 1.05 grams per milliliter. And then down lower on problem number 19, you also need to add some information. This is the freezing point constant of water. All right, in class, we have already answered number 7. All right, so we're going to proceed on from there. I'm going to just jump right in and try to go straight through as far as I can. I plan on making another vodcast in IC tomorrow as well, which is Friday. All right, let's get started. What is the molality, careful, of a solution that has 19.8 grams of magnesium chloride in 500 milliliters of water? All right, so refresher. Molality is not molarity. We got to be very careful. This is equal to the moles of the solute per kilogram of solvent. Solvent only. All right, so magnesium chloride is probably the one that's being dissolved. This is the ionic compound here. So I'm going to take the 19.8 grams, and we need to do some formula writing. So you need the formula so you can get your molar mass. Magnesium has a positive 2. Chloride has a negative 1. So this should be MgCl2. I'm going to convert this to moles because I need my solute in moles. Okay, so let's see. Magnesium's molar mass is 24.3. Chlorine is 35.5, and there's 2 of them. I got 95.3 grams per 1 mole. All right, so 19.8 divided by 95.3. I got 0.20. I'm going to try to stick to 3 sig figs, so this will be 0.08 moles. Okay. Water is always, when you're looking at a problem, water is most likely going to be the solvent, so try to just remember that he's usually the solvent. And what's the density of water? So yeah, it's 1 gram per milliliter, so each milliliter weighs a gram, so this is actually 500 grams of water. All right, so looking at the problem here, looking at what we need to plug in, I'm going to put the 0.208 moles on the numerator. And then the mass has to be in kilograms. That's very specific. So this may be 500 grams, but how many kilograms is that? How many grams are in a kilogram? 1,000. So think of it this way if you want. You'd probably want to go like this. There are 1,000 grams in a kilogram, which just means that you need to move the decimal 3 times to the left. So 0.208 divided by 0.500. I got 0.416, and this would be moles per kilogram. Final answer. Molality. Okay, let's move on to problem number 9. How many grams of solute are present in 1.5 liters of a 0.98, that's molarity, CaSO4. All right, so molarity is moles of solute per liter of solution. All right, so let's see what we've got. Looks like we have the volume and the molarity. Okay. So let's see, I'm going to go like this. 0.98 molar is equal to an X number of moles divided by 1.5 liters. All right, so let's get the moles. This would be 0.98 times 1.5. I got 1.47. If you are really, freaking out about your sig figs, I guess that would be 1.5 moles. But the question didn't ask us for how many moles, it actually asked us for how many grams. So this represents how many moles of calcium sulfate. So you need to just do one more step. We're going to change the moles to mass. Calcium has a molar mass of 40.1. Sulfur is 32.1. And then your oxygens are 14 each. I got a molar mass of 136.2 grams per mole. So 1.5 times that. 204.3 grams. Now, we should probably be sticking to this whole 2 sig fig thing. So look at this answer. 204.3. If you were only supposed to get 2 sig figs, 1, 2, what are you going to do? Reduce it to 20? Didn't you change the value? It's supposed to be in the 200s. You just reduced it to 20. So this isn't accurate. How do we get 2 sig figs out of this? How do we maintain the value? Scientific notation. To the second, and that would be grams. So if you were being all like super careful about your sig figs, basically you'd probably want to reduce this answer to 2 sig figs, and that would be 2.0 times 10 to the second. All right. Let's do problem 10. Okay, if I have 550 milliliters of a 6.5% by volume solution of ethanol, how many milliliters of pure ethanol are in the solution? All right, let me remind you of how to do that percent volume. What this would be is the volume of the solute, which in this case would be your ethanol, divided by the total volume of the solution. And times it by 100 to change it to a percent. Okay, so let's see what we do have. They gave you 550 milliliters of what? Of the solution. So down here we've got the volume of the solution. We have the percentage as well, so we have this guy right here. Kind of looks like they want to know how many milliliters of pure ethanol, which we said is going to be your solute. They want to know this numerator. Alright, so let's plug in everything together. 6.5% is equal to an unknown volume of your solute, because we don't have that. But we do have the total volume of the solution that they gave us. It was 550 milliliters, and then times it by 100. Let's get that numerator. My first plan of attack is if you see a times 100, I'm going to do the opposite. I'm going to divide by 100. So I'm going to just take this decimal, and this percentage, and change it to a decimal. And that's the same thing as like dividing by 100. Alright, so that's just reducing, getting rid of this by dividing. Alright, let's get that numerator. 0.065 times 550. I get 35.75, and I don't know, look at the original problem. It kind of looks like we need to reduce to 2 sig figs. So I'm going to reduce this to, say, 36 milliliters. Alright, so what this means is that if you have 550 milliliters of this solution, 36 milliliters of it will be pure ethanol. Alright, number 11. I need to prepare 3.2 molar NaCl solution, but all I have in my cabinet is 1 liter of a 10 molar NaCl. How much of the 3.2 molar solution can I make? They want to know how much of this I can make. Well, let's look. What do we got here? This is volume. What's this? This is molarity. What do we got over here? Molarity. And they want to know how much? Can you anticipate what kind of problem we got here? This is a dilution problem. Notice that the concentration over here is 10, and over here it's only 3.2. Oh, okay, so guys, dilution is M1V1 is equal to M2V2. Let's plug in what we got. Over here we got the 3.2 molar unknown volume. On the other side, we have a 10 molar solution and 1 liter. All right, notice that over on the right side, the unit here is liters. That's going to make this guy's unit liters as well. So whatever answer we get is going to be in liters. So I'm just going to take 10 and I'm going to divide it by 3.2. All right, so it looks like I am capable of making 3.125 liters. Now, guys, if you really want to be picky about your sig figs, over here this is only 1, this is 1, and that's 2. So I'd be comfortable with you giving me either 1 or 2 sig figs. So if you just said 3 liters, that would be perfectly fine. That works for me. So we can make about 3 liters of this 3.2 molar solution. All right. Number 12. Okay. So on number 12, you're leaving an 800 milliliter solution of a 0.75 molar uncovered on a windowsill. 45 milliliters evaporates. What's the new concentration? So if you start off with a container and you set it out and you don't put a lid on there, and the original solution has 800 milliliters, 45 milliliters evaporates. How do we calculate the final volume of the solution? What's the new volume? Part of it evaporated, right? What do you guys need to do? So the volume's going to go down. What should we do to get the new volume? Subtract. A lot of people think that the 45 milliliters is like the final volume. No. That's just how much we lost to the evaporation process. So 800 minus 45. This guy's volume over here is 755 milliliters. The original concentration was 0.75 molar, and they want to know what the final concentration is. So this is the same thing. It's a dilution problem. M1V1 is equal to M2V2. Original molarity was 0.75. Original volume was 800 milliliters. I'm going to change that to say 0.800. The second molarity we don't have, but the second volume is 0.755. All right, let's get that new molarity. 0.75 times 0.8 equals, divided by 0.755. Okay, second molarity, I got 0.7947. I'm thinking probably 2 sig figs would be about right, maybe 1 because of the 800 milliliters. I probably should have put a decimal on there. But anyway, so I don't know, probably 0.79 molar would be okay. If you said 0.8, that's close enough. But let's just make sure. Does this make sense? Did it get more concentrated? It should have, because when a solution evaporates, that's what happens. You're losing some of the water. So 0.75 was the initial, 0.79 is the final. So yeah, that makes sense. We're good. Oh boy, lots of fun here. We need to do the entire pH conversion. Alright, so one of those awesome things that I gave you, if you still have it, it's awesome. Let me show you. Yeah, you guys know what I'm going for? That crazy chart. Here we go. Here we go. Alright, take a screenshot. Like, pause, screenshot. Alright, so let's use that, okay? We want to solve for everything else, and this is just the first one from that problem set, okay? So we're going to solve for everything else. If I have the hydrogen ion concentration, if you look at this picture, you're here. I like from here to just go to pH. So what I'm going to do is I'm going to do the negative log of the concentration H. Alright, so pH is equal to negative log 1.0 times 10 to the negative 5. Hey guys, you have a base of 1.0! Isn't this like super easy? Do you remember that thing about how if we have a 1.0 in the front, it's like really easy? What's the answer here? It's 5. Ooh, yay. That makes it nice. Okay, so our pH is 5. How do we get pOH? Yeah, 14 minus 5. What's 14 minus 5, guys? 9. All right, and then let's see, the concentration of your OH ion. Technically what you would do on your calculator is you would go shift log, which would give you a power of 10, and then you go like -9, right? Hey, look at that. It's not a decimal. So actually that could be your answer, just 10 to the -9. That's the concentration of your OH ion. As long as this guy right here is not a decimal, you can do that. But what if it said like 9.5? Are you allowed to say 10 to the -9.5? No. That's something that you would have to punch in on your calculator. So the fact that it's just -9, you can actually report that as your answer because this means this, right? And then you're set. Okay, let's go back. Oops, wrong one. Okay. Let's do the next one. Okay. This time we give you your hydroxide ion concentration. So here's a trick question, or not a trick question, but a good way to review. You ready? If I go negative log 1.0 times 10 to the -7, what will that give me? Yeah, it'll give you pOH because you're looking at the OH ion. We've got to be really careful when we get on our test, okay? Just because you're doing negative log of something doesn't mean you're going to get pH. Watch what the ion is. OH ions give you pOH. H plus ions give you pH. Be careful. All right, hey, you got a base of 1.0. Super easy. What's the answer? 7. And that'll be your pOH. All right, what is the pH? 7. Yeah, nice. It's 14 minus 7. That's 7. All right, what is the concentration of your H plus ion? 1.0 times 10 to the -7, or just 10 to the -7 is fine. Notice that the concentration of the OH and the concentration of the H plus are identical. What kind of solution you got here? Neutral. Good job. All right, we'll do this one next. All right, let's do it. Okay, this time you have pH. And notice that it is not a whole number. We do have a little decimal associated there. So that beautiful trick that we were just doing, yeah, it's not going to work anymore, okay? So let's go back to the picture and see what we can pick apart. And it really doesn't matter which order you do it in. I've got pH right here. Why don't we go ahead and easily get pOH? That would be an easy one to do. All right, so what's pOH? 14 minus 8.3. Gives you 5.7. Easy. All right, so we had pH and we got pOH. It's just up to you how you want to go from here. I'm going to go ahead from the pH, I'm going to go down to H+, and from the pOH, I'm going to go down to the OH. I just like doing those. All right, so from here, I'm going to get my H+ ion concentration. And the way that you would do that is you would do that anti-log thing. So I'm going to go 10 to the -8.3, but I can't leave that as my answer because of that decimal in there, okay? So this time I'm going to grab my calculator, shift log, -8. And I got 5.01 times 10 to the -9. And you see this little -8.3? See how it's really close to 9? And that's how it always should be. So that's a great way to check your work. Okay? Let's do the opposite one. Let's do this guy. And what I'm going to do, this is your pOH. So to get to concentration OH, I would do 10 to the -5.7. So I have to do that on my calculator. You got that weird decimal thing going on. So shift log -5.7. And this one is going to give me about 1.995. Ooh. Hold on. 1.995 is no good. That's actually 2.0? 2.00, I guess? Yeah. Times 10 to the -6. All right, so there's your H plus ion concentration, there's your OH ion concentration, and there is your POH. All right. The more you do these, honestly, the faster you'll be at them. So this is great practice for memorizing your formulas for pH. All right, here we go again. H plus ion. So like I said, it really doesn't matter how you go through here. If I have the H plus ion, I'm going to give you guys a little bit of practice. Let's go from the H plus ion to the OH ion. Let's do it that way. And I'll test you, see if you do it right, okay? So this time I'm just going to switch things up. I'm going to solve for the OH ion. I'm going from H plus to OH. And there's a formula. The way you do it is you say 1.0 times 10 to the negative 14 on the top, and you divide it by your H plus ion concentration. It's 5.4 times 10 to the negative 5. All right, let's test you, see if you do okay. On my calculator, I'm hitting 1e negative 14 divided by 5.4e negative 5. I got 1.85 times 10 to the negative 10. All right, so there's the OH ion concentration. Just to mix things up, what I'll do is I'll come up here and let's get pH. All right, I can tell you that my answer will be really close to 5. Do you see that power 10, how it's got that negative 5? I know my answer will be close to that value. Here we go, negative log 5.4 E negative 5. Cool. Answer was 4.27. Oh, if you're worried about the sig figs, I suppose I should be reducing to 2. So I didn't really do that very well down here. I guess I should probably be saying like 1.9 down here. And then over here I should probably say 4.3, I guess. Okay. And then for POH, why don't you do negative log 1.9 times 10 to the negative 10? And I know my answer is going to be really close to 10. Negative log 1.9 e negative 10. And I'm really hoping that it'll make sense that my answer will be 9.7. And look at that, 4.3 plus 9.7, sure enough, it's 14. Good way to check your work. Just make sure when you're doing these type of problems that you're always kind of making sure things make sense to you. Oh my goodness, you guys want to keep doing these, or do you want to do a couple by yourself? Yeah, no kidding. Do a couple by yourself. I think it's good for you. Alright, then I'll skip to 14. Alright, write out the self-ionization of water and label the hydronium and the hydroxide ion. This came from a vodcast that we did way long time ago when I first taught you about the pH scale. It was in those guided notes. So, on the self-ionization of water. Water will naturally undergo an ionization process. Water will split into a hydrogen ion, but it'll also make a hydroxide ion. Okay, this guy right here is known as the hydronium. And you guys know this guy. He's known as hydroxide. Easy. Okay. Number 15. This is easy. I'm not going to do a problem on this separate sheet. Acids have higher what ion concentration? What are they known for making? Do they make hydroxides or hydrogens? Hydrogen ions. So you can call it hydronium, you can call it hydrogen ion, whatever. But acids will have a higher hydrogen ion concentration than the OH ion. So acids have higher concentration of H versus OH. All right, let's do number 16. Okay, what is the molarity of 100 milliliter calcium hydroxide solution that was titrated with 5.2 milliliters of a 0.1 molar hydrocyanic acid solution? First things first, you need the equation. Okay? Calcium hydroxide. So if you don't have it, you may want to pull out your periodic table, look at those ions, and make sure you get it right. So calcium is a positive 2 ion. Hydroxide is a negative 1. What's the proper formula? OH, yeah, 2, there you go. And then hydrocyanic acid, I swear I'm not trying to trick you. There's actually a there's a cyanide ion, yes. Anytime you see the hydro and the ick at the end, these come from ide ions. There is a cyanide ion, I promise you. Cyanide has a negative 1 charge, so how do you change them into an acid? Yeah, you're going to put hydrogens in the front. That's how we make acids. And so, remember, hydrogens have a +1 charge. All right, so you got a +1, -1. All right, let's get our products. This is an acid-base reaction. What are one of your products always going to be? Always. Yep, your water. And whatever's left is determined by, okay, the hydroxide and the hydrogens, that's what makes your water. But what's left will make the other ionic compounds. So the calcium and the cyanide are going to recombine. All right, so remember, calcium has a +2. Cyanide, that's a carbon nitrogen, that has a -1 charge. So what's the proper formula? Yeah, and it's polyatomic, so I'm going to wrap it in parentheses, okay? All right, you got to balance the entire reaction before we start that titration problem. And because I like to do this so much and because I keep ranting that all of you guys should do it, let's list the information provided in the problem underneath each. What do we know about calcium hydroxide? Well, we know that we've got 100 milliliters of it. They kind of want to know what the molarity is. The hydrocyanide, we know that it took 5.2 milliliters of a 0.10 molar solution to do it, to do the titration. So which one do you want to call your standard? Would that be the hydrocyanide or the calcium hydroxide? Yeah, the one that you know most about is that acid, the hydrocyanic acid. So always start with the volume of the stuff you know the most about, so I'm going to start right there. So guys, when you're going from milliliters to liters, how many times do you have to move the decimal? 3 times. But just to annoy you, because I like doing that, I'm going to show you the actual conversion. There you go. Milliliters is canceled. All right, remember, this is milliliters of the hydrocyanic acid. What do we do next? This is volume. What comes next? And it's a pattern. You have to cross-cancel liters. How do you do that? Do you guys remember what molarity is? It's moles per liter. You guys remember that? Cool. Next spot, molarity. If you have 1 liter of hydrocyanic acid, it will contain 0.10 moles in that solution. Okay. Look, you cross-canceled your liters. Nice. And this is how it always works. You will always start with the volume of the standard. Then next, you're going to do the molarity of your standard. So if you're wondering what to study, this is what you study. You study the pattern so that you know what the pattern is and you're always on top of that. What comes next? Because this is the next part. Right now you're on hydrocyanic acid. You're trying to get the molarity of the calcium hydroxide. You've got the volume, but what do you need for molarity again? You need his moles. How do I get that? You're on moles of HCN. Mole to mole ratio, that's right, and it comes from the balanced reaction. So the next critical piece is that mole to mole ratio. Follow hydrocyanic acid. If he's on the top here, he will be on the bottom over here. So every 2 moles of HCN that react, you will be able to neutralize 1 mole of the calcium hydroxide. This is just going to give you moles of calcium hydroxide. This is not molarity yet. So we're partway through the problem. How do we get molarity at the very end? What will I do once I get the answer on my calculator? Remember, molarity is moles per liter. This is just going to give you moles. You see how this canceled and that canceled? You will have moles of calcium hydroxide. You need molarity of calcium hydroxide. At the very end, you need to divide by that volume again. Okay, so coming over here. I know that I will be dividing by 100 milliliters is 0.100 liters of calcium hydroxide to get that molarity. So whatever the answer is, don't clear it and just keep it on your calculator and then divide by that volume, okay? Let's do it. 5.2 divided by 1,000 times 0.1 divided by 2 divided by 0.1. I'm not going to stop and tell you how many moles there were. I'm just going to give you the molarity. This is 2.6 times 10 to the negative 3 molar, and that is the concentration of your CaOH2 solution. All right.